All right, so this video is gonna teach us how to distinguish between SN1 and SN2. We have 4 different factors, as you've seen so far, when we're talking about these substitution reactions. That's the alkyl halide, or we can look at it as the electrophile. We also have the nucleophile, which plays a huge role in this substitution reaction. We have the leaving group, and then finally the solvent. So all of these play a role in the rate of an SN1 or SN2 reaction. All right, so what I want to do is create a chart for you. Let's check that out. So we got the 4 factors right here. SN1 for the alkyl halide, we're going to favor an SN1 reaction if we have a tertiary alkyl halide. Okay, the secondary alkyl halide I'm going to put in the middle, and then for the SN2 reaction, what we want to have for the alkyl halide is a primary or a methyl alkyl halide. Okay. And this is going to promote the formation or the mechanism, the SN1 mechanism or the SN2 mechanism if we have these. Okay. Now, in addition to that, SN1, we want to have a weak nucleophile, such as water, a neutral nucleophile. For SN2, we want to have a strong nucleophile, such as hydroxide, that negatively charged nucleophile. Now, if we have a secondary alkyl halide, we can go either way. That's why it's in the middle in no man's land. And so if we have a weak nucleophile, it's SN1. If it's a strong nucleophile, then it's SN2. Okay, simple enough. For the leaving groups, we always want to leave a good leaving group, because remember, this chart is all about promoting the rate or increasing the rate of an SN1 or SN2. Both of those want a good leaving group. And a good leaving group is a weak base. Okay. Now, for solvents, for SN1 reactions, we want to have that polar protic solvent, and that's because it's going to solvate the anions and the cations. Whereas the SN2 reactions, we want to have a polar aprotic. Now, don't forget, polar protic again is good for SN1 because it solvates both the cation as well as the anion. And the cation being the carbocation intermediate, and the anion being the leaving group as well as that nucleophile. So for SN2, however, we only solvate the cations, and so we don't solvate the anions, like hydroxide, for example, the nucleophile. And once, or since it's not solvated, that negative charge is almost like a naked negative charge. It is highly reactive, thus promoting or encouraging an SN2 mechanism. Okay. Now, for SN2, we also want to remember, just again, we're kind of just writing it a million times just so you get it. We never want a tertiary alkyl halide. We always want that strong nucleophile, and we want polar aprotic solvents, right? For SN1, we never want a primary or methyl alkyl halide. We want a weak nucleophile, and then we want a polar aprotic solvent. And these are all things that are going to promote SN1 or SN2, okay? So what about that secondary one, right? Well, we kind of mentioned, like, it could go either way, right? If we have the weak nucleophile, we're going SN1. If we have the strong nucleophile, we're going SN2. But it's kind of important to point out that this chart in general is all about favoring one or the other. If we have a weak nucleophile, we favor SN1 by decreasing the rate of the competing SN2 reaction. Okay, so they're generally going to be competing reactions, especially in this SN2. But one way is more favorable than the other, and by favorable I mean energetically. So the SN1's driven by electronic effects, while the SN2 is driven by steric effects, right? So if we can kind of create conditions that are favorable for SN1, then it is more likely to occur. Okay, so while we're on the topic of SN1 and electronic effects, let's talk about carbocation stability. You're going to want to put 5 asterisks by this. Okay, so 1, 2, 3, 4, 5. Okay, asterisks, star, whatever, highlight. This is important. The methyl is a carbocation that has a lower stability than a primary, which has lower stability than a secondary and tertiary, right? But the information that we haven't been given yet is these two central carbocations, right? They have the allylic carbocation as well as a benzylic carbocation. So this is the allylic, this is the benzylic. And these are both resonance stabilized, as you can see by these blue arrows, kind of showing you the kind of a transfer of charge, if you will, to the other carbon, or it's kind of a distribution of that positive charge over more than one atom, and so it's going to be more stable. And that stability is approximately equivalent to a secondary carbocation. Okay, so what that means is allylic and benzylic carbocations can react just like secondary carbocations, even though they are seemingly primary carbocations. Okay, so let's see this molecule right here drawn in green. We want to see which is the allylic and which is the benzylic. So try it on your own first, and then replay or restart the video, and then we'll go over it together. All right, so this pink carbon right here has a bromine on there that can act as a leaving group. And then it's also an sp3 carbon, so it's a possibility that substitution can occur, and it is next to a pi bond, so that is an allylic carbon. We have a carbon here that has a chlorine leaving group. Cool, so we can do a substitution reaction because it is also sp3, but if it were to leave, it would be a primary carbocation, and there's no resonance stabilization, so it's just a normal primary carbocation. I'm sorry, it's just a normal alkyl halide, a primary one, and that's not what we're looking for. This one right here is a carbon with a bromine on it that is a leaving group. However, that carbon is an sp2 carbon, and we were told eons ago that no SN2 or SN1 reactions can occur on sp2 carbons. Okay, that bond is just super strong, and it's also backside attack doesn't work for sp2, and then SN1 forming that carbocation, it's super unstable. It's more unstable than a methyl cation. So this by definition is a vinylic halide, so it's vinyl halide. And then we also have this sp2 carbon with the bromine on it. That is an aromatic or an aryl halide. And this guy right here is very similar to the vinylic halide in terms of stability or lack thereof, as well as the sp2 CBr bond that's strong. The carbon on the left is an sp3 carbon with a chlorine leaving group, and that checks out. That's cool. It's also connected to a benzene ring that does allow for resonance stabilization. Okay, so we got that resonance structure that by definition is a benzylic carbon. So notice that these carbons here, they are sp3 carbons with leaving groups on them, so that they can do substitution. But not only that, they also are adjacent to a pi bond, so that's where we get that resonance stabilization. And those are the key factors that allow us to differentiate between vinylic halides, aryl halides, and allylic and benzylic halides. Okay, so again, write that down. So the next thing we want to do is kind of go over the other factors pretty much. So we've got the alkyl halides covered. Now what we want to do is talk about the nucleophiles. Okay, so some common nucleophiles are chilling here right in this gorgeous looking chart. Oh my goodness. Yeah, it's really not all that. And it's definitely not all the nucleophiles. These are just some common nucleophiles I felt like throwing on a piece of paper for you. So a virtual paper. The red ones are, as you can see, are mostly negatively charged, except for the couple of those sulfur compounds and then the nitrogen, the amine on the right. But all the red ones are generally considered good nucleophiles, while the green ones, like water, the alcohol, and the fluoride, those are poor nucleophiles. Okay, and so we just kind of want to keep that in mind when we're thinking about the nucleophiles. Obviously, the negatively charged ones are going to be better than the neutral ones, but generally the sulfur compound, for example, is a larger atom than oxygen, for example, and so it's more polarizable, and that's why it's going to be a better nucleophile than its kind of congener is the term, so rather than the similar or analogous alcohol. Okay. So now we've got our leaving groups as another important factor, and what I did here was kind of put good leaving groups in one side and bad leaving groups on the other. Um, what I did was I also put the pKa's of the conjugate acids there for you. The one thing I want to point out is one of the leaving groups that's got the sulfur in it, that it's called para-toluene sulfonic acid, or abbreviated as TOSO minus for the leaving group, or TOSOH for the acid. Very common. Write it down, remember it. Great leaving group, okay? And also remember all the other good leaving groups. The bad leaving groups, as you can see, are negatively charged. They are going to have mildly acidic protons on their acid, the conjugate acid as well. Okay, so anybody bothered by the crooked lines in this terrible graph or chart that I made? This is me throwing my computer around and ripping my face off. Anyway, time for practice. I think every little thing makes me do that, and now rip my face off and then throw my computer now, just because I got that COVID heebie-jeebies or restlessness. All right, so anyway, the practice problem. What I'm doing is writing out a bunch of reactions, right? Obviously not the products, but what I want you to do is pause the video and try the reactions and tell me if they're SN1 or SN2, and then also draw the products. So let's see. I don't want to do that one. Burr. And this will be good. And then throw this guy right here, OTOS. Remember that guy was a great leaving group. All right, so go ahead and pause it, and then we'll run it through. So that's a secondary alkyl halide, a strong nucleophile. We aren't told what the solvent is, so that's okay. What we want to do is draw the inversion product, because that is a strong nucleophile. It's secondary, so it's SN2. We got another secondary alkyl halide with a strong nucleophile. Remember, DMF is dimethylformamide, so we'll just draw an OH. The difference is that we didn't have to draw the wedge in that case. We kind of just wanted to indicate that it was SN2. Since there was no stereochemistry indicated, then it doesn't matter, because it's not a chiral center. This one does have it, and it's a tertiary with a weak nucleophile, so we're thinking SN1. And we want to draw the racemic mixture. Remember, there's an inversion product, and there's also a product with the retention of stereochemistry. So basically, draw that with the chloride gone, and then the OH substituting that. Okay. Sorry, I wanted to change that. So we have the oxonium intermediate, that positively charged oxygen, and then a water molecule can come up and remove that proton to neutralize that alcohol, and this is the final substitution product. Now, I wanted to just kind of skip that part, but I think you guys should see it again before we start skipping that. We will definitely just call that a proton transfer in the future and move on with our life. You're expected to know what I mean by proton transfer, though. Okay, so here's the other product. Okay. Primary alkyl halide for that, primary alkyl bromide, more specifically, we have a strong nucleophile with the chloride in DMSO, a polar aprotic solvent. So we're thinking SN2. Now what we want to do is just pretty much substitute that bromine with a chlorine, and we're done. That's not a stereogenic center, so we don't have to draw any wedges or dashes. So all the work's done. Nice. This is a tertiary electrophile, essentially, with that OTOS leaving group. We have ROH, which is a weak nucleophile, and so we're thinking SN1, and that means we have to do retention of stereochemistry as well as inversion of stereochemistry. So what I do is just draw the product with the wedge and the dash, and then we're gonna skip that loss of the proton, but we know it's the mechanism like above in the water. So that we're basically just taking the R and the O and we place that on the dash, and then we'll draw another molecule in a similar manner with the wedge and the dash, but draw the OR group on the wedge. Okay, and there you have it. That's all she wrote. Now, I do want to say that this is just the beginning of our organic synthesis. We're kind of leveling up now. We see that these substitution reactions can kind of produce new products, right? We're making and breaking carbon bonds, and if we're making new carbon bonds, then we're building upon a molecule, and that's synthetic chemistry. We're making stuff now, and it's really important that we do understand the process that we're going through in determining these or distinguishing between these two mechanisms, because we're going to use those skills from here on out, and it's really important that we're kind of aware of the skills that we are applying here. Okay, and then more specifically to SN1 and SN2, I do want to remind you that we're distinguishing. SN1 is got the electronic effects, and then SN2's got those steric effects that play a role. They are competing reactions, and the conditions favor one or the other, although in theory both are possible. Okay, and that's pretty much it for SN1 and SN2. We'll have another video on some just general stuff, but let me know if you have any questions.